So I'd like to introduce the next speaker, Simon Doclo. And he actually got a PhD in the KU Leuven, and now in the professor in the University of Oldenburg. And I think in this audience, some of them are audio people. So for that, Simon is super famous. But for the speech recognition or other areas, I would like to say that Simon is a superstar in this audio area. And working on the most of the problem in the audio, like microphone array, speech enhancement, recognition, the reverberation, and so on, from theory to practice, including the binaural, the hearing devices. So it's connected to the previous Christian talk. And I usually ask my students if they have some problem in the audio issues. I ask them to read Simon's paper. Then we should have an answer. But this time we are lucky because Simon is here, so we can listen to Simon's great talk. Okay, thank you, Simon.
I think it's the first time somebody called me a superstar, so I'm not sure what to think of this. So the title of the talk is Blind Multi-Microphone Noise Reduction and Dereverberation Algorithms for Speech Communication Applications. And actually this last application, or these applications, will become important in the remainder of the talk. So as I don't have to tell, I think anybody in this audience, of course, reverberation and noise is typically jointly present in many acoustical environments. And in speech applications that will degrade the speech quality and the speech intelligibility. So if you look at some applications, of course, there's hands-free mobile telephony. But also I will focus on other applications, for example, more in the hearing instrument area, and in the, nowadays also would say, hearable area for normal hearing people. It's typically similar technology, middle, small twist, maybe small differences, which I will also focus on. What I will not focus on is actually automatic speech recognition. I've never worked on this actually. But of course also noise and reverberation degrades the performance of these kind of systems. And of course all these pictures are shown without wanting to make any publicity or favor one brand or another. So what are the objectives then in this area? To develop and derive some single and multi-microphone noise reduction and dereverberation algorithms. And I will focus in this talk on multi-microphone algorithms. As I already mentioned, I will mainly concentrate on speech communication applications. And in these applications, there are a couple of important things. First of all, it has to be online, meaning the latency between input and output shouldn't be too large, in the order of a couple of milliseconds. Blind, and what I mean by this is without any knowledge, of course, of where speakers are, even actually also without any knowledge about which microphone you use, where the microphones are located. And also, of course, everything is dynamic, especially for hearing aids, for example. People can move themselves, also the desired sources and the interfering sources can move. And maybe as a bit of a disappointment, or maybe as a bit of an odd presentation out, I will not focus on DNNs. I will actually focus on more traditional techniques, but at different stages of these algorithms, also, of course, DNNs can be used, and it can be interesting, of course, to discuss this later on in the discussion, I would say. So I will mainly present algorithms that exploit, or at least estimate, knowledge or models of speech signals and room acoustics, and also especially room acoustics. So in this presentation, more in particular, they will have three parts. In the first part, I will talk about joint estimation of both time-varying spatial and spectral variables, meaning so-called relative transfer functions, and PSDs, used for multi-microphone speech enhancement. In the second part of the talk, I will focus on binaural hearing devices, and I can skip a couple of slides because of the previous presentation, which is quite nice to save some time, where actually the main goal is not only to reduce the noise, or I would say enhance the speech, but also to preserve the auditory impression. So all the sources should actually come from the same direction as they were originally, assuming that we cannot cancel everything. And in the last part, it's a short part, I will also like to discuss some extensions to so-called acoustic sensor networks, in the sense that I will discuss the usage of these binaural hearing devices with remote microphones, which are spatially distributed in the room. So, without further ado, first part, joint dereverberation and noise reduction. And there will be a couple of formulas, but don't look at the formulas too much. I will guide you through. of course. So in this scenario, first of all, we consider quite simple scenario, single speech source in a noisy and reverberant environment, and microphones where we don't know the positions of these microphones. And if you look at the model in the STFT domain, can be other filter banks, of course, then the mth microphone at frequency K and frame L can be written as a convolution, also in this STFT domain, between the clean speech signal and the convolutive transfer function, and some ambient noise, which could be anything, could be interfering speaker, could be diffuse noise, as I will focus on, could be sensor noise. If we then split out this convolutive transfer function into the first term, this first frame, this actually more or less corresponds to the direct and the early part, actually, of the speech, which we would like to estimate. There's some late reverberation and some noise, and that's actually the interferent terms. Important to notice, all these quantities depend also on L, on the frame index, so they can be time varying. I'm likely assuming the sources can also move over time. And of course, the PSDs change over time. If we stack everything in one vector, then this can be easily written as the vector of observations is equal to, you could call it the steering vector, times the early and reverberant part in the reference microphone, without laws of generality, the first microphone, the reverberant part, and the ambient noise. So basically, the idea will be to, well, if you want to at least remove the reverberant noise, the reverberation, and the ambient noise to estimate this X1. And this vector A, I already said it's a steering vector. It's actually, we would call it typically a vector of relative early transfer functions. For people who have never heard about this, you can just think of this as a steering vector, and in an anechoic environment, it's just determined by the direction of arrival. In a reverberant environment, there's also early reflections that actually are playing a role in this vector. Okay, as I would say, or I would see things, but there are many other maybe classifications. There could be two main classes or two very popular classes of doing joint reverberation and noise reduction. One of them is doing beamforming a spectral post filter. So that just means you first have the microphone signals, you process it with a beamformer, and you also still have, which does the spatial filtering, and then you have a spectral enhancer. That's typically using this kind of model leading to, I will still briefly come back to this so-called multi-channel Wiener filter. On the other hand, I would say there's also techniques which not try to multiply STFT bins with a gain, complex valued or real valued, but techniques that try to subtract the interference from the signals. Actually, basically, directly also taking, or that wasn't good. Try to put it here, maybe. No. Should work. Yes. Okay. So basically, directly taking or aiming at taking the phase into account because they will estimate the noise and reverberation and then subtract it. First, in this first technique, for people who are not that familiar with it, maybe just one slide as a tutorial for, let's say, beamforming and spectral post filtering. Basically, all these microphones, these recorded noise and reverberant microphones, are then filtered and summed together in a filter and sum structure, and kind of what I would call the workhorse algorithm, which is very frequently used, is this so-called parametric multi-channel Wiener filter. The goal is actually quite easy. It tries to estimate the desired component in the reference microphone signal in this cost function. There's another term here, and you can trade off versus speech component, so distortion, versus interference reduction. In this case, very general, both reverberation and noise. The solution is well known. Depends here on correlation or covariance matrices of the speech and the interference, which you might be able to estimate, for example, using speech presence probability. However, as has been known for decades now, for a single source, it can be decomposed in an NVDR beamformer and a spectral post filters. Basically, having the same kind of performance where you split the spatial filtering in this NVDR beamformer and then the spectral filtering in the spectral post filter. And basically, it all comes down to estimating these quantities. So what do we need to estimate in order to implement this kind of beamformer and spectral post filter? We need to estimate this covariance matrix phi n. We need to estimate this relative early or relative transfer function A, and then the PSDs at the output of the NVDR beamformer. People who are not aware, there are some nice overview papers. Well, by myself, it's quite high level, but also by Sharon Ganot and other people in transactions in 2017. Okay, so now we still have to estimate all these quantities, and that's what I will present some work on in this first part of the talk. First, if we go back to our original model and plug it into these formulas and assume everything is uncorrelated, which is basically a crude assumption, but it kind of works well. And we also model the late reverberation as a diffuse sound field, which is also not really a bad assumption, at least if we then also take into account that the PSD of the reverberation is still a highly time-varying factor. Then we get to this formula, not that important, we just plugged in our quantities. And the key estimation tasks are now really estimating this RTF vector. You could see it as a steering vector. The PSD of the late reverberation, for which you can use different models, both temporal models as well as this multi-channel diffuse sound field model, and the noise covariance matrix. In the next kind of slides, I will present 3 techniques without focusing, as I said, on the equations, for estimating these PSDs, or for estimating jointly all these quantities, so the RTF vector and the PSDs. So first of all, one of these techniques is actually just estimating the PSDs, so of the clean speech and of the reverberation. And basically, in all the equations I show, without focusing on them, the red terms are the ones you want to estimate. The blue terms are the assumptions. And that's basically it. So if you want to estimate this PSD, so of the clean speech and of the reverberation, and assuming we know the RTF vector and the noise covariance matrix, you can first subtract this and then have this simple model where you can want to estimate these 2 quantities. Different estimators, or many different estimators, have been proposed, both maximum likelihood as well as easier models, which just actually put everything together in this model and minimize the Frobenius norm. And actually, in 2018, there were so many of these techniques available, we decided with different groups that we want to compare them in a good way or in a standard way. And as it turns out, that's actually the main result of that paper. All of them are more or less similar, which is good and bad, but that's actually what happens with these kind of techniques. So if you're interested in this, there's this nice overview paper, this overview paper at least, which we published in 2018. This is only estimating the PSDs. So what if you now, and that's what basically is really required, what if you want to estimate both the RETF vector and the PSDs? There's actually 2 techniques I want to briefly touch upon. One is still requiring an estimate of this noise covariance matrix, and now we want to estimate A and these PSDs. And it can be shown that by first pre-whitening this covariance matrix with the Koleski decomposition of the coherence matrix of the noise, so this diffuse coherence matrix, it can be shown that actually the eigenvectors and the eigenvalues of this matrix correspond very well to this RETF vector and the PSDs. So without proving this here, but this eigenvalue decomposition of this pre-whitened signal correlation matrix, from these you can actually estimate both the RETF vector, the time-varying RETF vector, and the time-varying PSDs. Another method actually went back to this Frobenius norm and says, okay, here I can only estimate these PSDs, but I want to estimate everything. So let's just do this. Let's just minimize this Frobenius norm and try to estimate all these quantities. It turns out there is no closed form solution for this, but it can be broken down into 2 subproblems, where for the PSDs, it's actually a very easily squares problem with a closed form solution, and for the RETF vector, it's an eigenvalue problem where you can estimate it based on the principal eigenvector. And then you iterate a couple of times, and basically you converge to the correct solution, at least if the model completely holds. Just as a comment, some people are a bit questioning the name, and I actually agree. Is this really alternatingly squares? There's an eigenvalue problem involved. So I would now like to refer it more to an alternating Frobenius norm minimization problem, because let's say some mathematical people said it's not truly an alternatingly squares problem. Okay, let's have some simulation results. And I said this was a very easy technique, so it's also not the best examples. I will play some better examples later on, actually. So this is just beamforming and spectral post-filtering, both, for example, for a stationary source, where we used some impulse responses from the ACE challenge from the database at 1.25 seconds, added with some simulated babble noise at 10 dB, and then also, I would say even more important or more relevant, moving source in our lab, where we can change the reverberation time from about 100 milliseconds to 1.2 seconds by just flipping these panels. We just put them at 0.35 seconds, and then we moved. There were different simulations, but I think in the simulation I will show, or in the recording I will show, the source is moving from 0 to 90 degrees with this microphone of 6 microphones spaced at 1 centimeter. Typical parameters, I would say sampling frequency 16 kilohertz, a very standard STFT frame length, and everything is, of course, updating at an online way. Okay, so without further ado, I will play some sound samples. So first, for just a simulated stationary source, this would be the input, also with some sensor noise and with some white noise there. Let's see if this works. It used to work, actually, before. This is always happening, of course. Yeah. This is strange, huh? It did work, eh? I did play some. Maybe I didn't check these ones.
Do you want to play them on your laptop?
Yeah, but maybe I'll play them at the end, if that's okay. I'm quite sure that the other ones work. Well, if they don't work anymore, then I will switch to my laptop. But that's very annoying. Okay, so, well, yeah. No, I will continue it first. Otherwise, it will take too long, and I'm sure that the other sound samples, they work. So, anyway, that's good. Second kind of technique, which is intrinsically, I would say, a bit better, because you don't just multiply the STFT bins. Yeah, thank you. Oh. Second technique, or class of techniques, which is intrinsically a bit better maybe, is at least if you use this subtraction, is really subtract an estimate of this late reverberation and the noise from the noisy and reverberant microphone signals. And that means instead of using this, let's say, approximate model, you basically really start from this convolutive model in the time frequency domain and use that to estimate the clean speech, or at least the clean speech component. So, as I already mentioned, now the goal is to start from this model. You still want to estimate the clean speech component from the noisy and reverberant data. And actually what it basically does is that there is some probabilistic estimation using models of the desired speech signal as well as of the acoustics, or you could say this reverberation. And as we also showed, and I will show also later on, it really will use some of the sparsity properties in the STFT domain. So using this kind of technique, many people will kind of know it or refer to it as multi-channel linear prediction or weighted prediction error. It really will try to estimate the clean speech signal as sparse as possible under some model of this late reverberation, under a model of the acoustics. Because we, of course, know, or most of you will know, that the reverberant speech signal is, of course, less sparse than the clean speech signal. Or you could say it also the other way around. So this kind of model can actually be transformed as follows. It can be transformed to an equivalent autoregressive model where basically the reverberant signal in some reference microphone is equal to the clean signal, including some early reflections, plus a sum of filtered and delayed microphone signals. That's basically what it does, and there are some details which are quite important. These delays, for example, in order not to pre-widen the signal too much, and these prediction filters, they have a certain length LG, which depends on the acoustical environment. And basically, since this model really holds, it's just basic math, we can estimate this clean speech signal if we can compute accurate, or in a good way, prediction filters, because then we just need to filter the signals, subtract it, and actually we get the clean speech signal. So that's the easy block diagram for this. We have microphone signals, we delay them with an appropriate delay in the STFT domain. We filter them, we actually try or aim at estimating the late reverberation or the noise, and then subtract it. Of course, the only problem is then, well, we still, of course, need to compute these filters. So how to select a suitable cost function for computing these prediction filters? And in 2010, I think that work kind of started in NTT. Tomohiro Nakatani, he presented a model based on a time-varying Gaussian model. And then a couple of years later, we extended this to a more general circular sparse prior. So basically what it is we assume for each SDFT coefficient a circular sparse prior or a circular super Gaussian prior, which can basically be written as a maximization over scaled Gaussians, where the scaling function can be interpreted as a hyperprior on the time-varying variance lambda. Seems a bit complicated, but if you then plug this into the equations, and assuming all SDFT bins are uncorrelated to each other, you can formulate a likelihood function, minimize it, and it turns out that optimizing this function or this procedure leads to an alternating optimization procedure for computing these. That's what you really need, these prediction filters, and also the time varying variance of the clean speech signal. If you use the circular sparse prior, there's still the scaling function in the update. But if you, for example, use quite general complex, CGG prior, complex generalized Gaussian prior with a certain shape parameter, we can actually change the shape parameter and try out different kind of circular sparse priors. For example, for a very small value, this is actually a very peaky, so very sparse prior, whereas for P is 2, this is actually just a Gaussian prior. And that's actually maybe the equations were a bit complicated for some people, but not for most, I hope. But it turns out that it was actually a nice thing that by using just this CGG prior, it turns out that this estimate of this variance is just this estimate of the D to the power 2 minus P, where in the original method P was 0, and now we can just change and play around a little bit with this P parameter. Without going into detail, this was the basic procedure. A nice thing that actually was shown in this paper, I think myself, is that it actually corresponds, this complete procedure, to just minimizing the P norm of this desired signal. So that's basically what happens. Of course, for P0, a zero norm is not really a norm, but you can still analyze it like this. So it really promotes sparsity of the time frequency coefficients across time in each frequency bin, still according to this autoregressive model, which really models the acoustics. We also had some additional work incorporating low-rank structure or having multiple outputs, and also recursive version for really updating these parameters over time when, for example, sources move, or you would have like a switching source scenario. Let's listen to some sound files, and I hope now this works. Well, these are the ones I tested. So we'll listen to just a clean signal. This was in a reverberant environment, 700 milliseconds for microphones. Typical parameters here for the STFT with for MCLP or WPE, whatever you want to call it, 8 taps per filter. So this is the clean signal.
They are rated single A1 by Moody's and single A plus by S&P.
This is one of the microphone signals.
They are rated single A1 by Moody's and single A plus by S&P.
And this would be the process signals after this procedure. Well.
They are rated single A1 by Moody's and single A plus by S&P.
Which is, at least, it's always difficult, as also the previous speaker said, playing back sound samples also for reverberation, for binaural. It's difficult, but at least I hope you heard the difference between the reverberant signal and that noisy, and the processed signal. Okay, so it's maybe a recap, or let's say not a recap, but what can still be done in this work, this first part of the talk. Of course, I only focused on the single speaker. So what we're also working on now is extending actually these procedures for estimating different RTF factors for multiple speaker scenarios, where in other work, people were only able to estimate the subspace of these RTFs, which is not sufficient. But there's now a paper under review where we also try to estimate or estimating these different RTFs separately, based on the so-called acoustics problem. Also, joint noise reduction and dereverberation in both the multi-channel linear prediction context. There's different approaches. We are proposing some approach where there's some cascade of 2 filters. I wouldn't say one for doing noise reduction, one for doing dereverberation, but still one is based on a traditional blocking matrix, for example, like in a GSE, and one is based on a delay, which is more referred to for the MCLP framework. At WASPA last week, there was also some other proposal from Tomohiro Nakatani to convert it into one filter and to jointly optimize it, which is also very nice work. We still have to check which one is the best or which one is performing more robust. Okay, so that's actually ends this first part of the talk. Now I want to move to binaural hearing devices. And basically, the same kind of techniques could be used for these binaural devices. They just have multiple microphones. But there is one thing which is completely different, or a major difference, is they will not have one output signal, but they need to have two output signals for both ears. And first of all, just to talk a little bit about hearing devices or hearing or hearables, I would say nowadays half of the population in New York is walking around. I had the impression with some devices in their ears, so hearables. At least for hearing devices, if you look at one hearing device, typically has 2 or 3, and most of them actually have 2 closely spaced microphones. So you could do some processing. But many people are also fitted with binaural devices, so on both ears, which wirelessly communicate with each other. And in the last part of the talk, I will also briefly say something about and even connecting it with some other microphones, smart phones, or some other microphones. I noticed actually the work didn't start. Started already quite some while ago, where we still had these kind of mobile phones. Yeah. So, what is the main objectives now of these kind of algorithms? Not only to improve speech intelligibility, so do noise reduction and dereverberation, but also to preserve the spatial awareness, or the spatial impression of the scene. Assuming we cannot cancel everything, maybe, we want to actually preserve the binaural cues, both of the desired source, but also of the residual background noise, if we're not able to cancel everything. The next slide, actually, I don't need, because also the previous speaker introduced is a little bit, what are these main binaural auditory cues? First of all, ITD because of the time difference, ILD, so interlevel difference because of the head shadow effect. But I just want to add one more to it, which is especially important in reverberant and multi-speaker environment, and that's called interaural coherence. So that's the coherence between the two ears. And this interaural coherence, or IC, it really describes the spatial characteristics, or the perceived width of a non-point source, so for example, of diffuse noise, or approximately diffuse noise. And it basically also determines when these ILD and ITD cues are so-called reliable for the auditory system. And especially in this part of the talk, I will focus on diffuse noise, and there this ICQ will become very relevant, because for diffuse noise, ILD and ITD cues actually don't play any role. They're not relevant for the auditory perception of such kind of noise fields. Okay, so this is the basic configuration. We have a hearing device on the left, on the right. Totally have M microphones. In this work, we still assume all microphone signals are available at both hearing aids. They're perfectly synchronized, so we don't cover synchronization issues. That's, I would say, something for the hearing aid industry. So we assume everything is available, and basically now the goal is to compute 2 filters. One for the left side, one for the right side, still using all of the microphone signals. So now we don't only compute one filter, as in the first part of the talk, but we want to compute 2 filters, W sub 0, W sub 1. There's 2 main paradigms, I would say. One is in order to both do noise reduction or speech quality, intelligibility enhancement, and spatial awareness preservation. One of these techniques is rather simple, but still definitely quite good, is to say, well, when I apply the same gain, real valued or complex valued, on both sides, the reference microphone on both sides, actually I will not change the cues of all sources. You will not change the ILD cues, definitely, ITD cue also not, but actually you will change some kind of inter-envelope cue. So, but basically it's still quite good if you can compute a gain with whatever spatial filter you actually like, even generating just a monaural signal, you can compute it on both sides. I would say that definitely preserves the binaural cues. There's possibly maybe some artifacts, although with all the newest technology available, I should maybe also cancel out this kind of negative point. putting this aside, we've actually made more focused on a different kind of paradigm, which is true spatial filtering, where we really compute two spatial filters, or spectral spatial filters, on both sides, both using all of the microphone signals and filtering all of the microphone signals. Where we can easily merge spatial and spectral post-filtering. The only problem is, as we will see now, is that if you use this in a standard way, the binaural cue preservation is not guaranteed for the residual noise. So this MVDR beamformer multi-channel Wiener filter, I explained it for let's say the monaural case with just one output. Basically, you can reformulate all these equations just for two sides, left and right side. Here also left and right side. So we'll not go into detail here. It has quite a good noise reduction performance. But what happens if you plainly use this kind of algorithms, binaural MVDR beamformer or binaural multi-channel Wiener filter, on these binaural hearing aids? Just to illustrate this, suppose we have this scenario where we have a user wearing two hearing aids. We have a source coming from the front and some diffuse background noise. That means for the signal from the front, or for the source signal, just the ILDQ is almost 0 dB, it's coming from the front. And for the noise, it's diffuse, so it can be shown that interaural coherence is kind of a sync-like function, a little bit different. Here I show this square of it, the magnitude squared coherence, so it's like a sync squared function, more or less. These are real recordings, so it's not, of course, perfectly according to theory. What happens now if you just apply plainly this binaural MVDR beamformer? Well, actually the noise will be reduced up to some point, but it will be perceived as coming from the same direction as a speech. So it would be you're walking in a busy street, there's sounds coming from everywhere, and then all this noise is reduced but being mapped to one direction. So you completely lose this spatial awareness when wearing these devices if you would just plainly apply the binaural MVDR beamformer, which is obviously not desired, and even in this situation is dangerous, because you might not be able to localize, for example, cars coming from a certain direction. So in the last couple of years, we've been working on different techniques, also aiming not only at preserving the cues of the desired speech source, but also of the residual noise. And in one technique, we really aim at preserving this interaural coherence of the noise. So we have this, let's say, standard cost function. We added something to it. It's a bit complicated. It's good to write a paper, but maybe not to implement in a real device. So we've also come up with something more easy, where we don't only aim at preserving the speech component, but just a scaled version of that noise component. And it's called partial noise estimation. That's just actually a term we have to do. It turns out actually the solution is pretty simple to also interpret. What it turns down to is that you basically have this binaural MVDR or MWF, not preserving the cues of the residual noise, and you mix in part of the input signal. At first that seems a bit strange because you mix in a really noisy signal, but in this noisy signal all the cues are preserved. So basically it comes down to, if you mix this in, how much should you mix in? If you mix in too much, of course, you will lose all your noise reduction. If you don't mix in anything, you don't have any spatial awareness. And there are different techniques that we proposed. If you really want it in a simple way, you just have a fixed value. Actually works pretty well, but it's not that optimal, of course. And we also have some more psychoacoustically motivated approaches. One of them is using, first of all, just frequency-dependent values, which are based on the discrimination ability of the human auditory system for interaural coherence. And basically, it has been shown by several psychoacoustic studies that if the interaural coherence is quite high, then you should also preserve it. It seems like more a localized source. If it's low, then you can actually mess it up a bit and nobody will hear it. So that's actually what it uses. It says if the interaural coherence is low, especially at low frequencies, then try to preserve it. Not perfectly, but really try to preserve it in some limits. If it's low, then you can just mess it up. So let's just look at some psychoacoustic studies which we actually did for these kind of algorithms. So we have, let's say, the plain binaural MVDR beamformer, and then it's maybe not that important for this talk, different procedures to compute this mixing parameter, both in a frequency-dependent way or time-frequency-dependent way. So for this we used some simulations. We had binaural hearing aid recordings, 2x2 microphones in a cafeteria environment. That's the Oldenburg database with binaural hearing aid responses. we had some realistic cafeteria ambient noise, and we used, let's say, on the one hand, just a plain binaural NVDR beamformer, and then these extensions where we mixed in different ways the inputs. We did subjective listening experiments, at that time with normal hearing subjects. Now we're also repeating with hearing impaired and CI subjects, cochlear implant subjects. And we both evaluated spatial quality using a Mushrat test, comparing to the input signals, and speech intelligibility by measuring the speech reception threshold, so the SRT, using a matrix sentence test. It was in Germany, so it was a German test, but it shouldn't influence any of the results. And then the main question we actually ask is, does binaural masking, so preserving these cues again, does it actually compensate for the technical SNR decrease by mixing in the signals again? That's the main question we wanted to answer with these psychoacoustic experiments. So first, spatial quality. So these are the Mushra results, where we just asked to evaluate spatial difference between the reference microphone signals and the binaural output signals. First of all the subjects seem to, well, or most of them seem to recognize the hidden reference. And then for the binaural NVDR, just collapsing everything to one direction, you can see spatial quality is very poor, as we actually expected also. And then for all the different mixing algorithms, there's different versions. You can see that for one of these versions is actually pretty close to the input signal. So spatially at least, these signals are perceived almost in no different way to the noisy microphone signals. So that seems good. That's at least what we wanted to achieve. Binaural cue preservation significantly can improve the spatial quality or awareness. But what happens now to the SRT? That's the next question. Well, yep, as we can see here, so this is speech reception threshold. So it's for normal hearing people to remember. So typically at the reference signals, it's something like minus 8 dB. We're pretty good as normal hearing people to actually recognize 50% of the words in a noisy scenario. If you look at the binaural NVDR, in this scenario, diffuse noise, that's also a normal number, it would increase this SRT. Well, that's going from minus 8 to about minus 12, or minus 7 to minus 11. It increases the SRT, so improves the SRT by about 4 dB, which is a well-known number also shown by other studies. And also by our extension, it pretty much stays the same. I mean, there is no statistically significant difference between also these mixing in algorithms and the original algorithm. So I would say almost in conclusion, well, you will gain the spatial awareness, the spatial quality, but you don't lose in speech intelligibility. You also don't gain in it, but that's basically also not what we want to directly achieve. Yeah, I have time for 2 sound samples, I would say. As also previous speaker said, binaural effects are very difficult, so if you're interested, just come to us and we can, of course, let you hear with headphones. But it's just to give you an idea about, let's say, the noise reduction performance. So that's the input signal.
A boy fell from the window.
This would be the output of a binaural MWF, but you will not hear the collapsing here, I guess.
A boy fell from the window.
And then we have a procedure that will mix in a little bit.
A boy fell from the window.
And so, well, you cannot hear, of course, the spatial impression, but I hope you heard that the noise reduction is pretty similar, actually, to the binaural MWF. Okay, in the last 5, maybe 10 minutes, 5 minutes. Always trying, right? I want to talk about acoustic sensor networks or using these hearing devices with remote microphones in the room. I mean, as people get more and more devices, more in the room, and they're also wirelessly connected, this would also give some advantage. So, I noticed that after a while my microphone dropped here. Somebody should have told me. But typically my voice is loud enough, I know that too. So we want to exploit these external microphones together with the hearing aid. It's not a first idea, of course, that we had. It's been around for a while. And so we want to integrate these external microphones with the microphones on the hearing device itself. And what I will talk about is just one aspect. It's actually to estimate this relative transfer function that I already talked about, exploiting these external microphones to steer a binaural NVDR beamformer. To actually estimate these coefficients here, these A vectors, in both the left and the right filter. And the idea is actually extremely simple, is that we call this the spatial coherence method. We assume that the noise component in the external microphone and the local hearing aid microphone is very small. And that actually is true for example, when the microphones are far enough apart, and that means 20 to 30 centimeters, nothing more, and assuming more or less diffuse noise. It doesn't have to perfectly hold, but if this holds, then actually this assumption is pretty good. And then looking at the correlation of the covariance matrix, if we look at the column corresponding to one or more external microphones, they will basically only have some information about the clean speech signal. So basically also this RTF factor is embedded in this last column. Typically people take the first column for estimating RTFs. We just took a different one in a sense. You can also show there is one element that's still a bit biased, but it's maybe not that important here. And actually it's a method that is very low complexity. You just have to compute this noisy correlation matrix, take the correct column, normalize in the correct way, and that's actually an estimate of your relative transfer function vector. That's all. Of course, we compared it also to more state-of-the-art methods. This covariance widening method that I already explained based on the generalized eigenvalue decomposition. And I will just show the results and then play in an audio sample to conclude the talk. So this is again our lab. We have 2x2 microphones here. We have one external microphone. In this case, it's at 1 meter. It's a bit further, but we have tried out different positions. And we have a moving speaker, which we simulated by really moving a loudspeaker. So we also have really the reference signal available. What it shows, and I will guide you through this graph, we had actually different positions. So the loudspeaker is moving away from this external microphone. If you look at the intelligibility weighted SNR improvement over time, the green curve actually just shows you the SNR of the so-called external microphone. So basically, if it's close to the external microphone, you have a perfect quality. But if you would stream that microphone to the hearing aids, you have no spatial awareness at all. You just have in-head localization. If it moves farther away from the external microphone, of course, the SNR drops. Then there's two bunch of algorithms. First, these dashed ones, which are just using the hearing aid microphones. And let's say the standard algorithm in many hearing aids nowadays is that are just steered towards the front, where it's also assumed, of course, the listener or the user will turn his or her head. But if we just fix it to the front, of course, it's okay if the source is coming from the frontal direction. The performance drops even to negative values if the source is not coming from the frontal direction. If you then estimate the RTF and just use the local microphone signals, at least the performance is more or less constant, not independent, but more independent of where the source is. If you then filter all of the microphone signals, that means the local microphone signals on the hearing aid and also these external microphone signals, we have the solid lines, blue and red, here on top. And as you can see, the performance is better than the external microphone signal, maybe not that much, but it's always better than the external microphone signal. And in addition, it will also preserve the binaural cues. So the source will also come from the correct direction. So actually, it looks a bit better than actually on this graph, both as an R improvement as well as a cue preservation. This slide I will skip. So we also had extensions for multiple external microphones, actually presented last week at WASPA. And there's also a demo I want to share you where we have real-world recordings. There's a speaker in an acoustical environment, a KEMA, so it's an artificial head with two behind-the-ear hearing aids with two microphones and one external microphone and some diffuse noise, which is played back by 4 loudspeakers in that lab. So I'll just play that video, and you can at least hear the noise reduction. For the binaural effects, you would have to contact me, and there's also a nice online demo. So if you see the student, actually, the PhD student, Nico Gusling, who is now in the room, he also has some nice MATLAB demo, which you can try out if you want to see this.
So first, let's listen to the unprocessed tuning device input signals, where we not apply any noise reduction, but with a spatial perception. That means you're localizing correctly now on the right side. You are able to follow that movement by listening to the voice. You are now localizing correctly on the left side. The overall goal now is to reduce the amplified background noise while preserving the spatial perception. The system will now can see, we can acquire a much higher signal-to-noise ratio, but the spatial perception is completely gone. You're not able to follow my movement anymore by listening to my voice, and you're not able to localize me correctly on the left side now. To counter this problem, we are now combining the external microphone with the head-mounted microphones and process all microphone signals together in a binaural noise reduction microphone. As you can hear by doing so, we apply a significant amount of noise reduction to the microphone signals and preserve the spatial impression of the acoustic scene. That means right now you're localizing me correctly on the left side. You're again able to follow my movement by listening to my voice, and are now correctly localizing me on the right side. For you to get an impression of how fast this algorithm is able to adapt to new speaker positions, I will now remain quiet and go back to the left side. And as you can hear, the algorithm is able to adapt to new speaker positions very quickly. But how does this work? What are we doing here?
Okay.
We are using the implementation of the binaural ER.
That's the explanation again of how it works, so I don't need to repeat this. Okay, so what is future work in this area? Of course, and I would also be happy to answer questions in that respect. This was a microphone on the shirt. We also have, of course, other simulations where the microphone is in the room. What happens with an interfering speaker? It's also a very interesting scenario. We're also looking more at practical aspects, synchronization and latency issues. That's the first question somebody from industry then asks, of course, what happens then? And even more complex and time-varying environments where we want to integrate some computational auditory scene analysis. Okay, so as conclusion, what I talked about today is really speech communication applications, where it's very important to have online algorithms adapting to the environment in a rather fast way without too much latency. I talked about joint noise reduction and dereverberation algorithms using multiple sensors, where one class of techniques, more traditional NVDR plus post-filtering, where we have to estimate the time-varying spatial and spectral variables. And then something I would say more advanced is reverberation and noise suppression. And then I talked about the application of these algorithms in binaural hearing devices, where the aim is not only to reduce the noise or to enhance the speech signal, but also to preserve the spatial awareness, which can be done by preserving the auditory cues of all the sources in the scene. And this can even be done better if you have access to remote microphone signals. Thanks a lot for your attention. No, there is also, well, there are also, of course, details in the system. There is also a speech presence probability detector in SPP, which is actually detecting when speech is present or not. So, very good question. Yeah. So, but it's then not detecting the SPP. And in this scenario, I'm quite sure that the SPP is just on the external microphone, so it's almost perfect. If you have multiple microphones, then it will be a combination of the SPP in the different external or in all the microphones. Yeah.
Okay. Thank you very much.